Now this shows you, for example, how we started our initial journey itself. We started on, as you are aware, on November 5th, we launched the satellite from the PSLV launch vehicle from Sriharikota, and then we went through a series of Earth maneuvers. Now today's topic is innovation. Now how innovation was introduced or utilized in these activities. See, unlike other space programs where the satellite was launched directly into the Mars orbit, we had to go through a series of earthborne maneuvers, primarily because we were having limited capability with respect to the launch mass and also the amount of fuel we can carry on the satellite. And also we made use of these initial earthborne operations to take advantage of interaction of moon and the moon's interaction with the orbit, change the plane of the orbit, so that we were trying every trick that was available to save the fuel and achieve the requisite orbit. As you can visualize, any object, if it has to be put into an orbit around a planet, what you need to do is take that object into a distance from the planet, and then at that point give it a velocity such that it can, if the velocity is less than the escape velocity of that planet, it will go around the planet. If the velocity is greater than the escape velocity of that planet, then it will go beyond the planet. So first, when we launched the satellite from the our launch vehicle, we had something like 240 kilometers by 24,000 kilometers, and progressively we increased the apogee point from 24,000 up to 2 lakh and then beyond. And in this process, we went through a series of activities which was necessary for us, because as you can visualize, when you take an object far away from yourself, one of the most difficult things in hand is how to communicate with it. Up to this point of time, the farthest we had sent an object was in the lunar mission, roughly about 4 lakh kilometers. Whereas here, we are required to send it to almost 250 million, and the farthest point during its mission goes up to 450 million kilometers. As the distance increases, one of the key things is how to communicate with it. And then the communication itself takes some finite time. And all of you are aware, the velocity of light itself is only 3 lakh kilometers per second. So if you take this 250 million kilometers, the signal what we send from ground will take about 12.5 minutes to reach the object. So because it takes so much time to reach, and then if you give a command, then by the time you know that a command has operated, it takes about 25 minutes. So one of the things is you cannot do any ground intervention during the operation. So one is you have to come up with a system which has a communication capability which can do at very large distances. Then you need to tackle the issue of not near real time, a time gap between the events. Now because of this, we had to build in the satellite a tremendous amount of autonomy. Now the autonomy requires that the satellite by itself decides whether it has a problem, and in case it has a problem, switch over to the alternate system that is available and make decisions. So when the actual Mars insertion takes place, we will be having no visibility of the satellite. So that means you have to make sure that the satellite has a set of memory systems on board where you can store the instructions and these instructions operate. And you also have a set of safety systems built into the satellite. So during our 5 Earth burns, what we did is we tried to rehearse all these features which was built into the satellite. In each of the consecutive operations, we brought in one more new element, and that element got verified. It was, of course, during one such verification process, we found that we had made a mistake on ground. That, for example, in this case, what happens is there is a liquid apogee motor which has got 2 coils for energizing. Just in case one electronic circuit fails, you want the second coil to come and operate. So there were 2 coils which were wound on the solenoid, And then both of them, when you operate independently, it works fine. But then when you operate them together, it doesn't work. So magnetic fields cancel each other and there is no force available for the valve to operate. So we realized during one of these earth burns that there was an error, and it also gave us an opportunity to replan and correct our maneuver strategy subsequently. So we made use of all these 5 earth burns to learn about the behavior of the satellite and also exercise all its redundancies, and then went ahead. On the 1st of December, we went into what is called a trans-Mars injection. Just to highlight to you the kind of innovation that was required, see, this was the propellant budget we had prepared prior to launch. We required for Earth operations around 1.5 kilometers per second, which consumes about 527 kilograms of fuel. Then Mars orbit insertion, it takes about 1069 meters per second. Then we also had kept provision for finite burn losses, then orbit dispersion, that is if the launch vehicle produces some error, how to compensate that. Then the trajectory correction maneuvers, we had kept about 35 meters per second. And similarly, you have attitude control and various other activities that required correction. And we were expecting to use about 850 kg of fuel, and what we had loaded was about 870 kilograms. So actually you can see that we hardly have any margin for error. Unlike other systems, other space programs, the difficulty what we had is, if at any time we encounter a problem which calls for additional use of fuel, we will be left with not enough fuel for Mars orbit insertion. That means you will reach Mars, but you will not be able to go around the Mars. So that was one of the key problems. So we had to find in each and every operation of ours a method by which we do it optimally, which consumes minimum fuel and also does not result in any errors in the operation. So that was the real actually challenge for us. And then today we can definitely say that all the features that were built into the satellite and the various processes we adopted have been successful. One of the things was in the launch itself, we had zero dispersion. The launch vehicle gave a perfect launch, so we didn't have to spend any fuel for accommodating the orbit dispersion. Then our earthburn operations also went through with flawlessly. Then Mars orbit insertion itself is one very key activity, primarily because in this, the scope for error is even less than the error margin we had for Mars orbit insertion. You can imagine that if an object has to travel about 650 million kilometers before it reaches Mars, then whatever direction you are giving, even if you make 1 microradian error, it will be in error by 650 kilometers at the end of its travels. So you cannot afford to do directional errors, so you have to control the orientation of the satellite very precisely. Then second thing we found is the liquid apogee motor itself has a predictable performance. Later we will see the details of the propulsion system, how it operates. But at this point, we have to predict the performance of the engine and then tell for about 30 minutes when it is firing what is the output it is going to give. We have to predict it to an accuracy better than 0.5%. Because what we found during trans-Mars injection, if we predict that it is going to perform in a particular manner, and actually if it overperforms, you have to correct again that overperformance by spending fuel. So you spend fuel of the order of 15 to 20 kg for 1% overperformance. Similarly, if it underperforms, then again you have to provide more fuel and correct that. So you have to take care of orientation, you have to take care of prediction of performance, and also you have to take care of when to cut off the actual burn. We will see some of the details in subsequent. Then the trajectory correction maneuvers, originally we had planned 5 such maneuvers during the course of traverse of 300 days. But what we found, the various activities were going on with such precision, we had to use only 2 of those correction maneuvers instead of 5. Then the orbitrizing itself, you saw the basic activity, how it does. Each time you fire the engine when it is approaching the perigee, and then at that point you increase its velocity and it goes further. Now like I said, we went through this multiple loop orbit, and we took advantage of the celestial interaction of gravity, and then we raised the plane of the orbit to about 22 degrees. Few of those degrees we were able to achieve because of interaction with moon. Then once the actual orbit of the trans-Mars injection was done, during 300 days, what is it that happens? That is one of the very interesting aspects of this mission. See, primarily what happens is, as you can visualize, if you are on a boat and a boat you have got a sail, because of the wind, the person who is steering the boat is able to navigate. While the satellite is in space, it receives radiation from sun, and this sunlight is sufficient to produce torque on the satellite, and this disturbing torque is actually compensated by, we have reaction wheels on the satellite, so those reaction wheels either speed up or speed down and compensate for the torque that is exerted on the satellite by the radiation pressure. But then the torque on the wheel itself, wheel speed cannot go indefinitely, so we have an upper limit and a lower limit. Once those limits are reached, we have to fire the thrusters and bring the wheel speed to a nominal operation. So each time you fire a thruster, you are actually giving a velocity to the satellite. So what we found is the solar radiation pressure was causing equivalent of 1 millimeter per second velocity to the satellite. So this 1 millimeter per second accumulated over 300 days will require correction by fuel of the order of 6 to 7 kilograms of fuel is required to be spent. And this depends on the orientation you keep of the satellite. There are some favorable orientation which reduces the torque, and there are unfavorable orientation which increases the torque. So one of our tasks was to ensure that the satellite orientation with respect to sun is such that this torque is minimized, and also the velocity you are giving to the satellite is also reduced. Then apart from this, we also may have to make sure that the satellite is in the visibility of Earth, and we have a number of ground stations which we will see in subsequent slides. So one of the major disturbing forces was the solar radiation pressure, and apart from that, any behavior of the satellite itself, if it loses track or if the thrusters have to fire by error, then they would have caused problem to us in terms of the orbit. Then after traveling from Earth almost about 600 million kilometers, you were to enter the sphere of influence of Mars. So during this period, what is important is, one was actually, we said, controlling the disturbing torques. Second was, you need to actually predict where you are going to be on a given day. That means on the 24th of September, where you are going to be is required to be predicted very accurately. So for that, what is done is, you do the tracking of the satellite by using ground station, and then you have a model which takes into account all the interplanetary forces, the gravitational fields of the Mars, and then based on this you predict where you are going to be on the 24th of September. The margin we had is, we should be in a range of 200 kilometers to 1100 kilometers above the Mars surface on the 24th of September at 7:30 in the morning. That was our target all along. So we need to determine the current position of the satellite, and then based on the prediction, find out where we are, and if this point is outside this range of 200 to 1100, then you have to do correction maneuvers. That was the target. And then when you reach the sphere of influence of Mars, what you mean by the sphere of influence of Mars is, if you take an object and place it between Sun and Mars, you will find a location where the gravitational forces of Sun and Mars on the object balances, and then from that point towards the Mars, you call it as the sphere of influence of Mars, and away from that the dominant force will be Sun. So we were targeting to move towards the Mars during this period. Now getting into this Martian orbit itself, what were the criticalities? There were a number of criticalities there. Of course, the prime thing is, to make sure that you are at the correct position on that day. Then second thing is you have to have all your resources available for doing the operation. And beyond that, you also had the difficulty that the satellite was going into the shadow of Mars. That means no sunlight is available during that period. So the power generation on the satellite will not be available at that point of time. Then there is also occultation of the satellite for an observer on Earth. That means you will not be able to get any communication from the satellite. So all these factors had to be taken into account in the planning. Then the dynamics itself is, see, the satellite is moving at that point of time in heliocentric mode about 22 kilometers per second, and relative to Mars it was moving at a velocity of about 3.5 kilometers per second. And as it enters the influence of Mars and goes towards the 24th September, its velocity increases from 3.5 kilometers to 5.6 kilometers per second. So this increase in velocity because of the gravitational pull of the Mars is one of the things which we needed to control. Because if you leave it at that velocity, the escape velocity for Mars is only 4.72. That means the object would go outside the Mars influence and go into deep space. So what we needed to do was, we needed to reorient the satellite and reduce its velocity by about 1.1 kilometers per second so that it comes within the capture range of Mars. So that was the other activity that was required. Then for this, we had to use one of the key subsystems is the propulsion subsystem. Now this propulsion subsystem itself is the one which we had been using all along for all our geostationary satellites, what we call a 440 Newton engine, which makes use of bipropellant. We'll see the details subsequently. And it provides an ISP of about 320 seconds. This is the particular subsystem, which is a very critical subsystem for us to ensure that the satellite gets the required velocity and operates. What you have here is a helium tank, which is used for pressurizing the two fuel tanks. One is a fuel is monomethyl hydrazine, and an oxidizer, which is a mixture of oxides of nitrogen. Now these two tanks, the green and the orange tank, contains these two fuels, and initially, as we said, they were loaded with totally about 850 kilograms. Now the key factors here is there is a specific ratio of fuel required between oxidizer and the fuel, and this ratio has to be maintained, and then the pressurant, helium pressurant, fills the gas on the tanks and then produces this force. Now the two liquids, when they come in contact in the engine, then you get the thrust. So initial phase we had spent during the transmars injection about 500 kilograms, and at that point we found that one of the pressure regulators in the system had developed some problem. So because of that, we had to shut down that complete segment and then operate the two tanks in what we call a blowdown mode. That means it was not a mode which was originally envisaged. In the original plan, the pressurants were going to make the flow of the liquids in a regulated mode. So everything would have been in a controlled fashion. So we had to make, because of this, we had to go through a large amount of simulation. So we conducted simulation tests at high altitude facility in Mahendragiri. We rigged up the entire system and then made sure that even in the blowdown mode of operation, we have sufficient velocity that we can get and then operate the system. Then the other problem was, see, at the end of transmars injection, to avoid the leakages, we had to shut down one part of the plumbing line, taking the fuel onto the LAM engine. This is because you want to ensure that there is no leakage of the fuel during this 300-day period. But then what happens is, when we come close to the Mars injection, we have to open a new plumb line path, and which has not been tested up to that point of time. So in one of the key things in space program is, any untested segment, if you are operating, you are running a risk. So we had to make a decision that whether we want to test this engine, LAM engine, which has taken rest for about 300 days, and also new plumb line which is coming in needed to be tested. So this was what was done on the 22nd of September. We opened that latch valve through pyrofiring and then made sure that the LAM engine operates, and then once that operation was through, the alternate plans which we had worked out, what we call plan B, was put to rest. Otherwise, we of course had generated an alternate plan. Even if the main LAM engine doesn't work, the 8 small engines which is showing the thrust now, using that we had worked out an alternate plan. And of course this required many changes in the way the onboard autonomy have already touched upon. Primarily, the satellite has to make all its decision on its own, because we cannot afford to do ground intervention for doing the operations, and all the operations are done in such a way that you have the basic set of commands uploaded early. And for the Mars orbit insertion, we had loaded these commands almost 10 days in advance. So even if you had a contingency that you are not able to communicate with the satellite could in principle have done all the operation, and if everything was successful, it would have got inserted into the Mars orbit also. So even to take care of ground contingencies, this autonomy is an essential thing. And we, during our subsequent mission times, we are also likely to face what is called a blackout and whiteout period. That means you will not be able to communicate with the satellite for pretty long periods of the order of 10 to 15 days, because what happens is the antenna which is looking at the Mars, in its field of view, if you get sun, the signal which comes in is so large that the other signal you will not be able to detect on that. And for some periods, Mars will go behind the sun, and during that period also you will not have communication. So in terms of achieving and one more important aspect is, while you have built all this autonomy and the safety modes into the satellite, the Mars orbit insertion itself is a one-time event. So you cannot afford to miss that. That means whatever firing of the engine is there, it has to happen at the cost of anything. So we had to disable all these safe modes. So during these periods, safe mode was actually not safe for us, because we would have missed the orbit insertion if any of the safe modes had operated during that period. So we had actually delinked all those operations during the Mars orbit insertion. Now basically what happens is, you have the command stored, and then it does all the limit checks, it decides which subsystem has failed, and then bring up the operation. Then there are different modes of acquisition, and one of the good things about this particular satellite is, apart from couple of anomalies what we had in the propulsion system, we did not face any problem in any of the subsystem. We did not have to get into any safe mode. So in fact, this was also one of the risky things as we reached near the Mars insertion, because you have not encountered such a situation. How will you manage such a situation if you encounter? Those were the issues that we were grappling just around the insertion time. Of course, communication we have already seen, that we had kept 3 types of communication, what is called a low gain antenna, a medium gain antenna, and a high gain antenna. Low gain antenna can give you almost 360-degree field of view, but it can work only up to 25 million kilometers for telecommanding and 7 million kilometers for telemetry. Whereas the medium gain antenna, which has a field of view of plus minus 40 degree, can give you about 230 million kilometers for telemetry and 200 for telecommand. And for the high gain antenna, for the full mission it can provide, but the limitation is it has only a field of view of plus minus 2 degree. That means even if everything is working on the satellite and the satellite direction is in error by more than 2 degree, you have no communication with the satellite, and then you cannot do anything with that. So you have to build some contingencies for that. So one of the things that is done is, if the satellite does not receive a command from ground for a predefined period, then it starts going about its axis, such that at some point of time it will cut the disk, and then you will be able to communicate. Then if we come to the set of instruments that are there on the satellite itself, now the role of which will be important, because now we are going to do various observations. One is a neutral composition analyzer, which can give you the particle, molecules and atoms, its concentrations it can detect. Then you have got a Mars color camera. You have a number of pictures which I will also show you. This is a 2K, a 4 megapixel camera basically. Then you have got a methane sensor which looks for methane in the atmosphere of Mars. And this is also a concept which is very different from what others have used so far, because we had the task of building these payloads in a mass of only 15 kilograms, and all these 5 payloads are built within that 15 kilograms, and also each of them should produce meaningful observation. And this makes use of what is called a Fabry-Perot instrument, and then has got very narrow band absorption band wavelengths incorporated in that, and it operates in the shortwave infrared region. We also have a thermal imaging spectrometer which provides 7 to 13 micron wavelength temperature surface mapping can be done. Then we also have a unit called a Lyman alpha photometer which actually measures the deuterium to hydrogen ratio, and by measuring this ratio one can get some inclination about the kind of how the water is lost on the surface of Mars. Some of the outputs what you have seen is, of course, the very first day, immediately after insertion, we had an opportunity to cover Mars without reorienting the satellite, because in its natural trajectory, Mars was being seen on the sunlit period. So we were able to get about 5 images that day. Then these are some of the images which are captured from this. These are craters seen on the surface of Mars. See, our initial insertion is such that the satellite is at the apoapsis, the Mars is sunlit. So as a result of this, full disk of the Mars you can cover. It also so happens that though many missions have been put to Mars, from the full disk coverage, large number of images, Mars has probably already taken more images than any other satellite so far of the full disk. And then you can see the kind of details one can get. This is overlaying the 2 consecutive days data sets. These are some of the images taken of Mars. And also you can see this is one of the enhanced images taken on 30th September. And this actually different coverage of the Mars you can superpose and see. This is also one very high resolution image of Mars. Okay, we have in this Mars color camera 3 colors, and you can see in the blue you can see distinct features, and this talks about actually the scattering of the atmospheric clouds or dust. So you can do a lot of science also using this color camera. And then we also have, it so happened that if you closely watch on the right hand corner, there is one black spot which is moving. If you are able to catch that, it is actually one of the moons of Mars, Phobos, which is captured. The shadow of that moon is falling on the Mars surface, and then this is captured in 4 consecutive frames with 12 seconds apart. So using this, you are able to clearly see that there is a shadow of Phobos. Phobos is only about 27 kilometers wide, and that image is also captured. This was captured on 7th of October. Okay. Apart from this, of course, the mission itself has produced a large amount of enthusiasm and feeling of pride in the entire country. On the day of the Mars orbit insertion, one of the schools had tried or organized a function like this. I'm just trying to show one of them, and similarly the other function. So basically what we are being able to achieve in this Mars mission is we are able to make use of the capability that we have today with us, a polar satellite launch vehicle, and then a satellite which weighs only about 1300 kilograms at the time of launch, and then using minimum fuel we have been able to reach Mars, and we have shown that it is possible to do planetary missions of the type of Mars using limited in terms of money, but not limited in terms of idea or innovations. the amount of innovative concepts that have been used in this particular mission is enormous, and that is why it has caught the imagination of the entire globe. And today we can definitely feel proud that we have been able to achieve this mission as originally planned without any major mishap. And today we have got almost about 45 kilograms of fuel, usable fuel, still on the satellite, and this satellite original plan was 6 months. We will be able to survive for much longer period than that today. And currently we are also engaged in one key event. On the 19th of October, one of the comets, what is called a siding spring comet, is going to come within a distance of about 135,000 kilometers from Mars. And this is probably one of the unique opportunities because an observer can be so close to a comet. So many of the instruments what we have put on this satellite will be making observations of the comet. And another thing is also, of course, originally when the comet was sighted, it was said that the comet tail would be so large and the tail density will be such that within 1 square meter, one particle will be there, whose size could be more than a millimeter or so, and it would be traveling at a speed of something like 54 kilometers per second. So at this speed, this particle can damage anything that it hits. So we had worry initially because our orbit is an inclined plane orbit, unlike most of the others, which is near polar, where in a near polar orbit, you can actually get to the other side of Mars during the tail coming and then get protection. Whereas in our case, we don't have such a possibility. We can get protection only from the solar flux or the ion flux, for which we have taken action, and the satellite is today moved instead of apoapsis position to periapsis position, and then the distance between the Mars and the Mars orbiter mission and the comet is about 140,000 kilometers. So this is a safe distance from the particle density, which also is told today is only 1/1,000,000th of a particle per meter square. So it's really not a big issue in terms of the particle or the dust particle that is coming. So other than that, all the 5 payloads have been operated, and other science payloads require significant amount of data analysis before you can come to the conclusion. So we are on a regular basis collecting the data. Our orbit is roughly about 3 days, and when we are at apoapsis, Mars itself rotates once in 24 hours, and we will be able to cover the entire Mars surface for various observations. With this, I thank you all for patient listening, and if any of you have any questions, I would be more than happy to answer. Thank you very much.